classical probability measure on mu, I will not repeat every time, but when I speak of probability, I will restrict to the special class of probability measures with moments of all order. So, if a measure has moments of all order, it defines a state on the star algebra of polynomials. State means that it is positive on positive elements and normalized to 1. The expectation is 1. Conversely, we know that if we have a probability measure on the, if we have a state, then we have at least one probability measure. It is a very well known in the theory of orthogonal polynomial that this measure will be unique if and only if the moment problem is determinate, for example, by Carleson criteria and so on. So, in the future, I will only discuss at the polynomial level. So for me, I will no longer speak of probability measures, which can be many, given the moments. I will only speak of the state on the polynomial algebra, which is unique. Such a state defines a scalar product on the polynomial algebra. So having a state on any star algebra, I can, of course, this scalar product is just the restriction of the usual L2 scalar product. And again, notice that the state is uniquely determined by restriction on the real filtration, on the real polynomial algebra. The connection with random variable is clearly done because we interpret this probability distribution, this probability measure on the real line, as a probability distribution of a real valued random variable. For this, we need to introduce a basis on the real line as a vector space, and it is well known that up to stochastic equivalence, any real valued random variable is uniquely determined by its distribution. So in this sense, we make a bridge with the classical probability. The cyclic representation of the star algebra is defined in the usual way. I give for granted that everybody knows cyclic representation essentially is the is regular representation of the polynomial algebra. But we will see in the following how it concretely acts. And we will use very often in the following this notation. When the identity, we consider it as an operator, we use 1. And when we consider it as an element of the vector space, we use phi0. So instead of writing this, which is long, we write simply like this to emphasize that we consider the polynomial algebra as a pre-Hilbert space. Okay. In the usual, now, in the following, for the Reconstruction Theorem, the following, so this is what I said. I can consider the polynomials in the quantum mechanical language will be the functions of the polynomials in the position operator. And I can consider them either as operator on multiplication on the pre-Hilbert space or as elements of pre-Hilbert space. When I want to emphasize elements, I will write multiplication like times action on the unit of the cyclic vector. Okay? And for example, you see, x to the power n is the multiplication operator, and x to the power n times phi0 is the vector. Now, of course, given the scalar product that we had before, since the algebra is commutative and the random variable x is real valued, This is position operator for those who come from quantum mechanics. Just the multiplication operator is symmetric, which means that you have this standard property of the scalar product. The important point is that this symmetry property characterizes those states on the polynomial algebra which are induced by a measure. So the theorem is the following. If you have a prescalar product on the polynomial algebra, then there exists some probability measure, or equivalently some state on the polynomial algebra, such that the scalar product is implemented by the probability measure, by the state, if and only if the position operator is symmetric with respect to the scalar product. And in this case, the state is uniquely determined by the standard operation that you can see. The proof is very simple, and it is, where is that chalk? Here, here. It is simply because if the operation, remember that the scalar product, if I have two monomials, monomial means in the one-dimensional case is simply xm times xn, then this scalar product will be this. So you see, this is the kernel is given then by commutativity, and the fact that this is self-adjoint, it will be like this. And it is positive definite. This kernel is positive definite. By a well-known theorem on the moment problem in probability theory, the condition that this kernel is positive definite as a two-variable kernel in M and N is sufficient for the existence of a probability measure. So if I have, let me be more precise. If the state is symmetric, I can write this like 1 times M. If this operator is symmetric, is M plus N and 1. Okay? So since it is symmetric, I can write this again like 1 xm xn 1. And since this is a scalar product, this kernel depends on the sum and is positive definite. And therefore, by the moment problem, there exists a probability measure, and the probability measure gives the state. Now, we have given the polynomials, of course, in one variable, every polynomial is a linear combination of monomials. So we have a direct sum because of the principle of identity of polynomials. If two polynomials are, the monomials are linearly independent, we can say. So the sum is direct in the sense of vector space, and is algebraic in the sense that it's finite. And now we want another kind of gradation. We want a so-called orthogonal gradation. The monomial gradation is independent of any state on the algebra. Now, I want to define this inductively, and for a reason that will be clear not in this lecture but in future lectures, I want to work not at the level of Hilbert space but at the level of pre-Hilbert space. The standard way that you define orthogonal polynomial in the literature is that you have the monomials you have the monomials, and you are in a Hilbert space, L2 of R with the measure mu, and you orthogonalize this sequence using Gram-Schmidt. What is the problem? The problem is that when you make orthogonalization procedure in the standard way, the result you obtain will be strongly dependent on the measure. For example, if the measure has finite support, you will obtain a finite dimensional subspace. I want to work at the pre-Hilbert space level, not for love of complications, but because I want to find a universal model for arbitrary measures. And you will see that this universal model is a familiar object in quantum mechanics. It's nothing but the Fock space. Okay? So that is why I want to work at pre-Hilbert space level. So suppose by induction that we have constructed a sequence of orthogonal polynomial. You should think that this phi j intuitively is the Gram-Schmidt orthogonalization of the monomial of degree j. So x to the power j, you subtract the components on all polynomials of degree strictly less than j, and you obtain the orthogonal polynomial with respect to j. How can we do this at the level of pre-Hilbert space? This is, I will go rather quickly on this first part because it's more algebraic, and if somebody is interested, I can give you the file to read, or if there are questions, I will answer. So you can. One important point is this. Think of the standard procedure of Gram-Schmidt. How do you orthogonalize? You subtract the component. But we know that the monomials are symmetric. So if we start from monomial and we subtract components, we always remain in the real Hilbert space because the components of monomials are real numbers. This will have an important consequence in the following. So suppose that I have formed a sequence of, I take the monomial of degree j, I subtract the component of this monomial on the space of lower order polynomial. Then I have two possibilities. Either I obtain a vector of zero norm for the pre-scalar product, or I have a non-zero norm and therefore I can normalize. Okay? So if I have a non-zero norm, the inductive step is made in two parts. First, I define the sequence of vectors, which have either norm 0 or norm 1. And then I define, always inductively, the projector, which is surjective projector onto the from all possible polynomials considered as a vector space onto the polynomials of degree less or equal than n. I use this notation, which is standard. This is in physics, this is bra vector, and this is the rank. This is the functional associated to the vector phi. And this is with respect to this given scalar product. Okay? So this is bra vector in the. So I consider the monomial of degree capital N. I subtract the component on the inductively defined projection. This is the inductively defined projection. And I have two possibilities. If I have not norm 0, I normalize. And so I can define the orthogonal projection in the standard way. Remember, phi star this is the rank 1 projection associated to the unit vector phi n. If it is 0, the norm of the nth monomial, then I will define the non-normalized ant vector. So essentially, look, this is a very important point that will play an important role, and you will understand it better only when, why is this so important when we go in multidimension. You see, when you orthogonalize a monomial of degree n, you obtain, you are subtracting a polynomial of lower, strictly lower order. So if you start from a monic polynomial means with the highest coefficient equal 1, you still get a monic polynomial, okay? So you do, the message is that you don't affect the highest degree when you orthogonalize, okay? So if Xi is a arbitrary vector in the an arbitrary polynomial, we use the monomial gradation, not the orthogonal gradation. But we know that the gradation is direct, so the coefficients Xn are uniquely determined and linear functions of Xi once Xi is given. Therefore, I can define inductively the projection in this way. This will be a zero norm vector. But in this way, I obtain a projective. So I always keep the degree to the maximum. Okay? The fact that I already mentioned it, by induction, phi j are polynomial with real coefficients, and the monomials and the multiplication operators, the multiplication by x is symmetric. Therefore, this scalar product is real. This means that the new projection that I have defined maps the real subspace into the real subspace. I want to check. There is yes. I will give less details because otherwise we will not. Okay, this is important. The filtration is increasing and it converges to 1. So let me, since the time is very short, I want to, maybe I will make a panoramic and then we go back and go in more detail. The panoramic is this. Suppose we have constructed inductively the increasing filtration of polynomials. Therefore, if I define this is the projection onto the, so this defines the polynomial, the projection onto the nth orthogonal polynomial. You see, the polynomial gradation will be the algebra considered as a vector space, and I will have now an orthogonal sum of C times phi n. N is in n. These are the orthogonal polynomial. Now, I want to use a more general language which will make the transition to multidimensional case immediate. So I will not exploit the fact that this is a rank 1 in this lecture, okay, for the moment. So, okay, so now these polynomials are orthogonal, these projections are mutually orthogonal, and they are a partition of the identity. And the sum, this is important, the sum is equal to 1. Since the sum is equal to 1, I can write any operator, in particular the multiplication operator, as a sum of P m x P n for all m and n. When I don't write means in the natural integers, okay? what is called the famous Jacobi three-diagonal relation is that apparently these are infinitely many matrix elements, but in fact, let me multiply on the right the multiplication operator by one fixed n. So all this will disappear because they are orthogonal, and only one index n will remain.
Confused with notation.
This
second line, that the p subscript n.
Pn are orthogonal projections.
Projection, not function.
Onto the nth space of this gradation.
They're not polynomials. They're actually projections.
They are?
Projections.
Yeah, orthogonal projections. Because now we have fixed the state. We are in the cyclic representation of the state. The scalar
Possibly zero.
Possibly they are zero. Possibly they are zero. I want to keep this freedom. Okay. So now for each fixed n, I have this identity. You see, this sum is still infinite. Okay. The theorem, famous Jacobi theorem, is that this sum is not infinite, but has only 3 terms, which is this. Okay, so this is the famous Jacobi relation. In fact, this is what I would call symmetric Jacobi relation. In the standard books is usually called, this is not what is usually found in the literature. Orthogonal polynomial is found, we will come later on, it's called the monic Jacobi relation, what you find in the literature. But the monic Jacobi relation supposes already that the measure is infinite support. Okay? And we will see that also for application to physics, it is very important to keep measures with finite support. Let me anticipate. For example, the Bernoulli measure, which has support on 2, is at the root of not only fermions, but also of Q-deformed commutation relation. So they are interesting for application. So let me keep this relation. How to prove this relation? In our case, remember that these are rank 1 projections, so they project on this vector. So essentially, what you want to prove is that if you have an element in this space, so a multiple of phi n, and if k is strictly greater than 1, the scalar product will be 0. But this is obvious by definition, because what is this phi n plus k? This is the monomial of degree n plus k minus the component on the strictly less, on the polynomials of degree strictly less than n plus k. But by assumption, k is strictly greater than 1. So this is in the component which is orthogonal to this. Okay? So in the language of polynomial, this will be written in the language that p, if we write Pn, P, so we write Pn plus k is equal to 0, and taking adjoint, you will have the difference, you exchange the indexes here, and this means that we obtain the same result for k strictly less than k, than 1. For k for k negative and less than -1. In this way, we simply exchange the role. Here there is the larger degree and here the smaller. If we take adjoint, the smaller will be here and the larger will be here. The conclusion is the same. They will be orthogonal. Maybe you can lift off the screen and I will continue only with the blackboard. Is possible? Yes, because I think it will. I will turn it off. Okay, I did. Okay, so now let us exploit the fact that these are one-dimensional projections. So you see, remember, in our language, P n is phi n orthogonal. So this is, can you see or not? It's possible. Can you see? So let us take the symmetric Jacobi relation and look at this part. So we have this on the left-hand side, you have this xpn. xpn. On the right-hand side, well, before this, before going to one dimension, let me say a last remark. So look, what is this projection? This takes, this gradation is a polynomial of degree n. So this takes the space Pn and brings to P n plus 1. So it's very natural to denote it by a daga n. Okay, because it increases the degree. This leaves the degree invariant. So it's very natural to call it a0n, because preserves the gradation, preservation operator. Because this maps Pn into itself. This, as you see, is the adjoint of this, with n rescaled, because it is, this is from n plus 1, from n to n plus 1, and sorry, this is not correct. This has to be the correct, because I am summing over m here, n is fixed here. You see? So this is n and this is n minus 1. So this goes from n to n minus 1. So this is annihilator. We will call it an. Okay? Therefore, what we have proved that x multiplied by Pn, x multiplied by Pn is equal a daga n plus a0n plus a minus n. Okay? Now, let us sum over n. We obtain that this is a partition of the identity, so the sum is 1. So this, we obtain x is equal sum over n, a daga n, plus sum over n, a0 n, plus sum over n, a minus n. So let me call this a daga, this a0, and this a minus, and we obtained what we call the quantum decomposition. So what we have proved that every random variable, classical random variable with all moments, has a canonically associated decomposition into three operators which remind very much the creation and standard creation, preservation, and annihilation. So this we will call the CAP operator: creation, annihilation, preservation. Now we go to we want to have a better insight on how the structure of these operators. So we exploit the fact that an is a plus n is creator pn plus 1 x pn, pn plus 1 x pn. Remember that Pn is the rank 1 projection. We are in one dimension. You see, all this discussion you will see is true in many dimensions. In one dimension, this is a particularly simple form because I multiply and here by phi n plus 1. And here I have a rank 1 operator which takes something from n and brings to n plus 1. Okay? The creation, as you see, is essentially adjoint up to a minus n is taking pn minus 1 here, x p n, and so it will be phi n star phi n minus 1, and here will be x phi n and phi n minus 1. So this will be creation, and of course preservation is the diagonal part. So this is phi n x phi n and phi n star. So let me call now the diagonal part is a number, is a real number. We call alpha n. Let me call alpha n. Off diagonal part, look, these are very similar, only that here is the higher one and here is the lower one. But here we exploit the symmetry because if we write the lower one, phi n minus 1, x phi n, we use the symmetry first, and we write x phi n minus 1 and phi n. Then we use the fact that scalar product is real, and so we again write phi n x phi n minus 1. So you see now it looks like this, but scaled by 1. You see? So that is why we call symmetric Jacobi relation. If I call this number beta n, then this number will be beta n minus 1. And so we obtain finally the symmetric Jacobi relation, which is well, here I wrote separately, but remember x is the sum of these three. And in fact, it's convenient to use this one, xpn, because if I multiply by phi n, now pn phi n is equal to phi n, and I obtain x phi n equal beta n phi n plus 1 plus alpha n phi n plus beta n minus 1 phi n minus 1. So you see, this is a symmetric Jacobi relation. Symmetric because you see the highest degree and the lowest degree have a coefficient which belong to the same sequence but just shifted by 1. This beta is a very important number. Its square, I will anticipate that its square is what is usually called the principal Jacobi sequence and denoted omega n. Omega n, because it's the square of a real number, is necessarily positive, and alpha n, the alpha n, which is the preservation number, is real. Preservation number is important in probabilistic meaning. It measures how much this sequence is completely arbitrary. So this is positive, but this is completely arbitrary. And there is a famous reconstruction theorem called the Favart theorem that we will discuss directly in many dimensions, that says that for every choice of Bn and An, Bn is real, we will see that in our specific case is also positive. In a moment we will, well, I don't think we will have time to see, because I want to arrive to show how this will generalize quantum mechanics. So maybe I will jump some part, and if somebody is interested, I will go back. So alpha n can be arbitrary, and beta n is the famous Favart lemma tells you that the converse of the statement is true. However, given two sequences, beta n and alpha n, real sequences, then there exists a state on the polynomial algebra. So this beta n square is called the principal Jacobi sequence, and alpha n is called secondary Jacobi sequence. Okay, now we have shown that this form of the Jacobi relation is a symmetric Jacobi relation. Let me use this one, the operator form, because it will give you more insight. Because remember, I am summing over, to get x, I am summing over all this. So now I know what is this form of A daga n. It has this form. So I can write this quantum decomposition directly in a kind of a spectral form. Spectral form will be for the diagonal, and in terms of rank 1 operators for the off diagonal. So I will write the quantum decomposition x simply replacing in this decomposition here to an, I will replace beta n and this projection. So not rank 1 operator. So this will be the beta n and phi n plus 1 phi n star plus sum alpha n phi n star plus sum beta n minus 1 phi n minus 1 phi n star. By definition, we put beta of minus 1 is equal to 0. You see? Now, from this you can immediately calculate. Remember, this is what we call A plus. This is what we call A0, and this is what we call A minus. From this relation, you immediately compute the commutation relations. Because if we apply, you see, A plus increases the degree by 1, and A minus decreases by 1. Therefore, both A plus, A minus, and A minus, A plus leave the gradation invariant. Since the gradation is one-dimensional, it must be a number, an eigenvalue. What is the eigenvalue? You compute easily, because this will go into phi n plus 1. A daga applied to phi n will go to beta n, which is a scalar, so I can bring it out, and the phi n plus 1. And then I apply a minus. But A minus gives beta n minus 1. So this is again beta n, because it will act on n plus 1. This is why, from where the positivity of Jacobi coefficient comes, from the commutation relations. You see, this is equal beta n square phi n. Okay? And if you do the converse here, you first go down, so you go to beta n minus 1. And then you have a daga here, and it will act on n minus 1, because I start on a phi n. Okay? On phi n. So I reproduce the square again, but minus 1. Beta n square minus 1 phi n. And so we have the commutation relation that A minus A daga restricted to the polynomial of degree n is equal to beta n square minus beta n square minus 1 phi n. So let us introduce the number operator, the preservation operator, which is characterized by the eigenvalues. Is like the preservation operator, but this preservation depends on alpha n. I want a universal object that will express all preservations. So I introduce the number operator, which is simply phi n star. This is lambda. By definition, this is the definition of lambda, and therefore, in terms, so for any Borel function, if I take capital F, if a Borel function, I define by spectral theorem f of lambda, the fn phi n star, and therefore I can take beta as a sequence, is a function, so I can write the commutation relation A minus A daga equal beta square lambda minus beta square lambda minus 1. And this is now operator form. You see, these are the generalized commutation relations associated canonically. You see, we did not put anything by hands. We only deduce it starting from the theory of orthogonal polynomials. Okay, example. Example, the Gaussian. The Gaussian is symmetric. I told you the alpha, I don't remember if I finish it, but there is a famous theorem that tells you that the secondary Jacobi sequence is identically 0 if and only if the measure mu is symmetric. So the Gaussian is symmetric. It has alpha n is equal to 0. Beta n, what is beta n for the Gaussian? Beta n square is equal n. So you see, this is an operator, but only for the Gaussian, this becomes beta, so beta lambda is equal to lambda for the gamma. Beta square lambda is equal lambda. So here you have lambda minus 1, which is 1. And you have, for the Gaussian, the commutation relation, which are exactly Heisenberg commutation relation that you recognize. So you see that the Heisenberg commutation, by the way, it happens that the only difference from the point of view of Jacobi sequences between Gaussian and Poisson is that in the Poisson case, beta n is the same as Gaussian. The only thing that changes is that Poisson, of course, is not symmetric. So here is not zero. But in the commutation relation, the secondary Jacobi sequence does not appear. So all measures in the same equivalence class for the equivalence relation of having the same Jacobi principal sequence, all these measures have the same commutation relation, and therefore the same Fock space. You see, this is Fock space in what sense? We have this gradation which is one-dimensional. So if you, in the language of quantum mechanics, this is the Fock space over the complex number. The one-mode Fock space is not necessarily boson. Why? Because if the measure has finite support, this is finite dimensional. Okay? Okay, so this is the measure. I have the time to show you how can we go, how the idea is now, what kind of quantum mechanics will correspond to more general measures. In the last part of my series of lectures, I want to discuss a program that we are doing since many, many years, which is called Nonlinear Quantization. This has to do with the old problem to define powers, local powers of fields, which, as you know, hits against the problem of renormalization. Okay? But this suggested a new approach to this problem when you do the second quantization of this procedure that I will discuss in the future, what I want to say? I want to say that this generalization of quantum mechanics is not just purely mathematical. It corresponds. For example, take the cube of the Gaussian or the fourth power of the Gaussian. Imagine that you can do this for fields, not only in language of probability theory, for stochastic processes, not only for single random variable. Then you would have a natural idea to define a commutation relation to higher powers of the usual field, which will correspond to the Gaussian case. I will in the future tell in more detail. So the philosophy will be this. The idea is, if we develop quantum mechanics for more general measures than Gaussian, for example, Gaussian to the fourth corresponds to the field 5 to the fourth in the literature, then we will obtain here some system which are very simple in the Jacobi coordinates of the new measure, but they can be extremely complicated in the Jacobi coefficients of the first measure. Let me be concrete. If I take the Gaussian, the Jacobi coefficients are very simple. Okay, in the literature, up to very recent result that we obtained with some collaborators, and I will speak about this, it was not known if what are the sequences alpha n and beta n for powers of the Gaussian if the power has order greater or equal than 3. For power 2, everybody knows that the square is the Gaussian. The square of the Gaussian is the gamma function. And the principal Jacobi sequence, we know the principal Jacobi sequence will go like the square of n, asymptotically. But starting from 3, it was not known. So this algebraic approach allowed to solve all the problem of classical probability. Given a random variable, and given the two Jacobi sequences of this random variable, what are the Jacobi sequences of a power of random variable? To give you an idea of the difficulty, there is a famous book by Chihara on orthogonal polynomials, in which this problem is solved only for the square and only in the case that the random variable is symmetric. So for 0 secondary Jacobi sequence, okay? And the proof is not trivial at all. It uses a rather heavy analytical machine. But we now, in the symmetric case, we have a half a page proof in purely algebraic language. So what is the idea? What is the idea is the following. Suppose now we would like to do a kind of generalized harmonic oscillator. So generalized harmonic oscillator, the Hamiltonian for harmonic oscillator is well known, is a plus, a minus. So if we consider this kind of generalized harmonic oscillator, and we consider the evolution and the EITH, E minus ITH of some operator. For example, we know, let me consider A minus, for example. And then I call AT this, by definition. This is the evolved under, but now the only point I am in a situation in which I have this commutation relation, okay? So let me use the standard notation, omega lambda minus omega lambda minus 1. This is the standard Jacobi notation. Okay, so you solve this equation as you do in usual quantum mechanics. So you take the derivative of AT, this is Heisenberg evolution, and this will be E minus ITH. And 1H comes here, A minus, and here is minus, there is I also, minus A minus H. So remembering that H is this, you find the commutator of A daga, A and A minus. Well, maybe it's better to put this plus. Maybe plus is okay. So you know that this is equal to A daga. No, so this is I put plus, so I put plus here, and so A daga is out. A minus A plus. And we know that this is equal this operator. So we have this operator omega lambda minus omega lambda minus 1. Okay. Now you solve the equation and you find that AT, you see, the derivative is simply it's convenient to do because there is a non-trivial point. AT is equal EI. I is also outside. But then there is this commutator that now we have computed, and here is again EITH. Okay, so E minus ITH. Then we have this operator, A daga, omega lambda, which is an operator now, no longer like Heisenberg, which is a scalar. However, you see, this leaves the gradation invariant. And this omega is by definition a function of the preservation operator, which also leaves the gradation invariant. So they commute. Okay? So this will commute with this factor. And this allows to reproduce the equation. And the initial condition is the annihilator. We are calculating a creator, a t at time 0 is just creator. Therefore, the solution will be simply the power series. The AT will be equal A daga T will be equal A daga E I T omega lambda minus omega lambda minus 1. In this sense, the exponential is in the sense of the spectral theory. You see? So you recognize this is the generalization of the harmonic oscillator evolution. However, you see, this is now a product of operators. In the standard harmonic oscillator, the exponential factor is a number. It's a function of number, but it is let me write it. The creator is the adjoint of the annihilator, so it has this operator factor on the other side, E minus and you see that the commutation relations are preserved. So we have an isomorphism of the algebras. And therefore, by standard theorem of algebra, it extends to the enveloping algebra, universal enveloping algebra, which is nothing but the algebra of all polynomials in A and A daga. So we have constructed a star automorphism of this algebra, which is the analog of the free evolution. Okay? And, okay, now I have run out of time, but I suggest you to do a very nice exercise. Write the Kubo-Martin-Schwinger condition for this evolution, and you will find the solution of the analog of equilibrium state for this evolution. And the equilibrium state, as you obviously can expect, will be the E minus beta at inverse temperature beta, omega lambda minus omega lambda minus 1. Here I should divide by the normalization. But of course, the normalization will be the trace of what is here. And now, of course, when these are integers, you have a convergence, see, geometric series, the well-known Planck factor. But in general, you will have that z bit is the sum of E to the minus beta of omega n minus omega n minus 1. And of course, for a lot of probability measures, this will be divergent. This means that, like in many situations in classical probability, you will not have an invariant state, but you have an invariant weight. For example, take the symmetric random walk in one dimension. It has not invariant state, but it is invariant weight. The Wiener process. The Wiener process has Lebesgue measure, has invariant weight, but no invariant state. So this will be reproduced here. So you can go far. And one open problem I want to mention, I am working now on doing the second quantization of this. What will be? You see, the difficulty is this. Here you have a difference, which is discrete. In order to find a good analog in the continuum case, what will be this difference? You may guess that it will become a derivative. But this has to be deduced. You cannot put by hands. This is an open problem. Thank you.
Since he's going to do a series of lectures, we can talk to him. He's here in 323 in his office.
I.
Thank you.
So when did you do your program?
It is 120.